Question 18 from section 1 of the 2017 Higher Physics examination from the SQA. A circuit containing a capacitor is set up as shown, and the supply has negligible internal resistance, and the maximum energy stored in the capacitor is, and we're given 5 possible choices. So we have got to find out first of all the potential difference across the 120 ohm resistor, and that will be the voltage across the capacitor, and from there we should be able to work out its energy. So we have the capacitance and we have the potential difference across it. So our first port of call is to examine the circuit and just pretend the capacitor is not there. So I've highlighted the circuit as shown, and we're going to work out the potential difference across the 120 ohm resistor. Now the 480 ohm and the 120 ohm resistor are connected in series, and therefore we can use the voltage division rule, which you can find in your higher relationship sheet, to find the potential difference across the 120 ohm resistor. So there's a formula there. You can see there's 2 formulas available, but the one we're going to use is the top one, and that is the V1 is equal to R1 over R1 plus R2 divided by the voltage of supply. So really that kind of type of circuit is a voltage divider circuit. So let's go ahead and work out the potential difference across the 30 microfarad capacitor, or across the 120 ohm resistor, and we'll call that V1. So V1 is equal to just simply R1 over R1 plus R2, and we have to do a big bracket around that and multiply that by the voltage of the supply, Vs. Now we know that we can write the following. We can say that's going to be resistor R1, and that's going to be resistor R2, and the voltage of supply is going to be over here. It's going to be 6 volts. So now we can plug in the numbers. So V1, the potential difference across the 120 ohm resistor, is going to equal to the first resistor R1, 120, divided by 120 plus 480, put that in a bracket, and I'm going to multiply that answer by the voltage supply, which is 6 volts. So all we have to do now is just rearrange that fraction. So it's going to be 120 all divided by, and it's going to be 600 multiplied by 6 volts. So you can see quite clearly we've got a 600 and a 6 here. We can cancel the 6 out there to leave us with 100. So 120 divided by 100 is going to give us 1.2. So now we know that the potential difference across that 120 ohm resistor, which will be the potential difference across the 30 microfarad capacitor, is 1.2 volts. Now we know the potential difference across it, we must seek out an equation which is going to give us the energy. And there's the 3 energy equations from your higher relationship sheets. You can see we've got a half QV, we have got energy equal to half CV squared, and we've got energy equal to half CQ squared over C. The one we're going to choose is the one ringed. That's going to be E equals a half CV squared, because we've got the capacitance value C, and we now have the potential difference V, 1.2 volts. So all we have to do is plug in the numbers. So E is going to equal to 1/2 CV squared, which is going to be equal to 1/2 times the value of the capacitance, which we know is 30 microfarads, and we'll write that as 30 times 10 to the minus 6, and we're going to multiply that by 1.2 squared, and that's going to give us a value for the energy. Do that in your calculator and you end up with 2.2 times 10 to the minus 5 joules. So the capacitor is going to store 2.2 times 10 to the minus 5 joules, and we look at our responses. That's going to be answer E. So our answer to question number 18 is E. Question 19 from section 1 of the 2017 Higher Physics examination from the SQA. A student makes the following statements about conductors, insulators and semiconductors. Statement 1. In conductors, the conduction band is completely filled with electrons. Statement 2. In insulators, the gap between the valence band and the conduction band is large. And statement 3. in semiconductors, increasing the temperature increases the conductivity. And we're asked to say which of the statements is or are correct. Now, band theory, we have to think first of all of what a conductor looks like. And there's the band theory diagram for a conductor. You can see that the area shown in the red down here is a filled up shell of electrons, and up here is the valence band. But the valence band has got space so that electrons can be promoted from the valence band into the conduction band. And that's what makes a conductor such a very good conductor, because the valence band is almost with the conduction band. I tend to think of it as like football stadiums. You have this tier completely full, but the next tier you have all the seats here full, but it's very easy to access these seats up here. So some of the supporters in these seats can move about the conduction band to find a seat which is going to be more viewable for the game. So therefore that's how we can view a conductor. So the very first statement says, in conductors, the conduction band is completely filled with electrons. Well, that's a wrong statement, because it's not completely filled with electrons. So we can mark that one wrong right away. What about statement 2? In insulators, the gap between the valence band and the conduction band is large. Well, we take a look at the insulator. You can see that that is true, because the valence band is completely filled up here, but there's an energy gap which the electrons must accomplish and must go over in order to get into the conduction band, where there are plenty of, as we can use our football stadium analogy, plenty of free seats. So the valence band here is filled up, but they can't really go anywhere because they can't reach the conduction band. So statement 2, in insulators, the gap between the valence band and the conduction band is large. Well, that's a true statement, so we can mark that true. That's going to be a true statement. What about the last one? In semiconductors, increasing the temperature increases the conductivity. Well, we look at the semiconductor band diagram. You can see that the valence band is completely filled up, but the conduction band is empty, but the energy gap between the conduction band and the valence band is actually quite small. Now, this means that if you actually add thermal energy to the valence band, some of the electrons actually can scale the energy gap and get into the conduction band, where, to use our football analogy, there are plenty of free seats and they can wander about, therefore constituting a conductor. So our answer for our statement number 3, in semiconductors, increasing the temperature increases the conductivity. Well, that is true, because the conductivity is the ability for the electrons to move, and if you heat this particular semiconductor up, some of the valence band electrons will gain enough energy to jump the small energy gap and be in the conduction band, where they can move freely about. So we can say that that statement is going to be true. Let's go back now and look and see what the combinations are. We have 1 only, so we're looking for 2 and 3 only, and you can see that will be answer E down here. So our answer to number 19 is going to be answer E. Only 2 and 3 statements will be correct. Now, as a step for a hint, you have to learn those diagrams, those band diagrams for the conductor, insulator and semiconductor. And a little hint is, think of football stadiums. Think of the 2 tiers in a football stadium, where a small ground like the semiconductor, supporters can easily climb up into the top tier, whereas in a big football stadium like Wembley or Hampden or something like that, then it's much more difficult for an insulator, for these seats, these supporters, to climb up into the top tier. So think about it that way, and study the conductor, insulator and semiconductor band diagrams, and have a mental picture of those in your head to answer these questions. Question 20, the last question from section 1 of the 2017 Higher Physics examination from the SQA. Astronomers use the following relationship to determine the distance d to a star. F equals L divided by 4 pi d squared. For a particular star, the following measurements are recorded. Apparent brightness F equals 4.4 times 10 to minus 10 watts per meter squared. And the luminosity L is equal to 6.1 times 10 to the power 30 watts. And based on this information, the distance to the star is, and we're given our 5 responses. So really we have to find the value of d, and we have to rearrange that equation there. So we start off with an equation. it is F, which we know is the apparent brightness, is equal to L, which is the luminosity, divided by 4 pi d squared, the distance to the star. Now, to get d squared on its own, we must cross multiply first of all and get F times 4 pi d squared, and that's going to equal to L. We want to find d squared on its own, so d squared on its own will have to divide each side by 4 pi times F. So d squared equals L divided by 4 pi, I'm just putting the 4 pi in the front now, and times F. And finally, d on its own will be equal to the square root of this value here, L divided by 4 pi F. So there we have the expression, the equation to find the distance from the star given those numbers. So all we have to do is plug those numbers in. So we know that d will be equal to the square roots, just leave that like that now. L is going to be 6.1, so it's 6.1 times 10 to the power 30, divided by, and put a bracket down here, 4 times pi times F, and F is going to be 4.4 times 10 to the minus 10. 4.4 times 10 to the minus 10. Don't forget to take the complete square root of all that. Now, you should be able to do that in your calculator, and we end up with a value of d equal to 3.32 times 10 to the power 19, and distance is going to be measured in meters. So if we write that into two significant figures, we get 3.3 times 10 to the power 19 meters, and that's going to give us answer number A, a letter A. 3.3 times 10 to the power 19 meters, so it's going to be A for our final answer for section 1.